Signals and Systems Sampling Theorem series on Signals and Systems, lecture number 2.21. In the area of signal processing, there exists two domains, time domain and frequency domain. In time domain, again there is a division into continuous time signals and discrete time signals. These two are related, that is, continuous time signals and discrete time signals are connected to each other. A discrete time signal can be generated from a continuous time signal by undertaking a process, a method known as sampling. When certain conditions are satisfied by the process or method of sampling, then the derived or generated discrete time signal carries all the information that is there in the continuous time signal from which discrete time signal is generated. Sampling theorem gives total information, complete information pertaining to the process of sampling. Especially, it gives the condition that is to be satisfied by the sampling rate when discrete time signal carries all the information that is there in its generating continuous time signal. In the present session, the focus is on sampling theorem for band limited signals, for band pass signals, and also we spend some time on the historical development of this particular theorem. Now let us move further to start the core session. We start the session by mentioning a few facts regarding the development of the sampling theorem. The Nyquist-Shannon sampling theorem, this is the exact name of this theorem. In short, we used to call it sampling theorem. This theorem serves as a connecting bridge between CT signals and DT signals in signal processing. CT stands for continuous time, DT stands for discrete time. As already mentioned, discrete time signals, they are generated, they are derived from continuous time signals. In real life, signals are mostly continuous time. So the source signal is continuous time signal. It is converted into a DT form so that it can be processed by digital systems. In the real world, signals are continuous time nature and systems, available systems are discrete time in nature. If we want to have the facility of processing signals with discrete time or digital systems, then we need to convert CT signals into DT form. The basic principle underlying the conversion from CT to DT form is sampling theorem. Let us move further. The name Nyquist-Shannon sampling theorem honors Harry Nyquist and Claude Shannon. The theorem was also previously discovered by E.T. Whittaker. He published his findings in 1915 regarding this theorem, and thus this theorem is also known by the names Whittaker-Shannon sampling theorem or Whittaker-Shannon and Whittaker-Nyquist-Shannon, and is also be referred as cardinal theorem of interpolation. These are a few points regarding the great people who contributed for the development of this theorem. Now, regarding theorem, it specifies a sample rate that permits a discrete sequence of samples to capture all the information from a finite bandwidth CT signal. As already mentioned, DT signal, it is derived from CT signal with the help of a process known as sampling. Sampling is associated with a rate, it is called sample rate. Sampling theorem, it specifies the rate, sample rate, so that DT signal carries information, complete information that is there in the CT signal. The theorem also leads to a formula for perfectly restructuring the original continuous time function from the samples. Strictly speaking, the theorem applies only to a class of mathematical functions having Fourier transform that is 0 outside of a finite region of frequencies. Intuitively, we expect that when one reduces a continuous function to a discrete sequence and interpolates back to a continuous function, the fidelity of the result depends upon the density or sample rate of the original samples. Notice the process of sampling. It is the one which derives DT signal from CT signal. Sampling process, it is associated with one parameter, critical parameter, that is sample rate. It is the sample rate which determines the quality of the signal that is recovered from the DT sequence. So sample rate is an important aspect pertaining to conversion of a CT into a DT signal. Some more aspects pertaining to sampling theorem. The sampling theorem introduces the concept of a sample rate that is sufficient for perfect fidelity for the class of functions that are band limited to a given bandwidth, such that no actual information is lost in the sampling process. It expresses the sufficient sample rate in terms of bandwidth for the class of functions. Perfect reconstruction may still be possible when the sample rate criteria is not satisfied, provided other constraints on the signal are known. In some cases, when sample rate criteria is not satisfied, utilizing additional constraints allows us for approximate reconstructions. The fidelity of these reconstructions can be verified and quantified using Bochner's theorem. Before going further, one has to have a very clear idea regarding the role of sampling theorem in signal processing. To understand this aspect, consider a signal, CT, continuous time signal. It is converted into DT form using a system or a process called sampler. Sampler does the sampling. Now this dt, discrete time signal, it is processed. The processing may be amplification, the processing may be removal of noise, or it can be anything. So the processing is done by digital system. Digital systems are cheap. Digital systems add less noise. They are efficient. They are associated with several advantages or benefits when compared to analog systems. So systems are mostly digital. To be able to use digital systems, continuous time signal here has been converted into discrete time signal, and it is processed by digital system. Output of this digital system is DT signal, and it is to be converted back into CT form. Integrator is one such circuit capable of converting DT signal into CT. Other circuits may also be there. Example is, one example for such a conversion circuit is integrator. Now the CT signal can be used. The CT may be a sound signal or audio signal. So audio signal is first converted into DT form, processed. After processing, again it is converted back into CT. If CT, original CT is music, the output of all this process again is music. The quality of the CT signal music at the output terminals depends upon the sampling rate here, and this rate is given by sampling theorem. With this understanding, now let us move to the theorem, actual theorem. In case of band limited signals means low pass signals. Beyond certain frequency, the signal strength is 0 or negligible. So in case of band limited signals, what is the sampling rate? A band limited signal which has no spectral components above frequency FM edge is uniquely determined by its values at uniform intervals Ts less than or equal to 1 by 2 FM. So this is the theorem proper, sampling theorem proper, applicable for band limited signals. It states, it gives information regarding the duration between samples, or it gives information regarding sample rate. It says Ts should be less than or equal to 1 by 2 FM. Notice FM is highest frequency in the signal. Larger than necessary values of Fs or smaller values of Ts, called oversampling, have no effect on the outcome of the reconstruction, but have the benefit of leaving a room for a transition band in which HF is free to take intermediate values. Larger than necessary values of Fs or smaller values of Ts. This process is called oversampling. It has no effect on the outcome of reconstruction, but it has the benefit of leaving a transition band. Undersampling means lesser than necessary values of Fs or higher values of Ts. It is called undersampling. It causes aliasing it is not in general a reversible operation. What he is telling here is undersampling results in loss of information. Now, a small explanation regarding the points that are mentioned here. Consider a CT signal like this. It is a signal S of t, this is t. Now, one can generate a DT signal with the values of this signal at specific uniform intervals. Let us say this is 3 seconds, t equal to 3 seconds. Then take sample of the signal at 4, then 5 seconds, 6, 7, 8. With these samples, one can generate a DT signal like this sequence. The sequence and CT signal both have same information, both can carry same information, or DT signal can carry the information that is there in the CT signal, provided the duration between the samples it is less than or equal to 1 by 2 FM, or sampling frequency is sampling frequency Fs. It is more than or equal to 2 FM. Some more points regarding band limited signals and their sampling. It can be observed the spectrum of sampled signal consists of original signal and its several replicas. So this is original signal. When it is sampled, its spectrum. When it is sketched, it appears like this. Notice the original signal is there in between 0 and FM. The next replica starts at Fs minus Fm and ends at Fs. From Fs to Fs plus Fm, there is another replica, original signal. It is not difficult for us to understand that the original signal can be obtained by using a low pass filter whose cutoff frequency is in between Fm and Fs minus Fm. Using a low pass filter, the original signal can be extracted without distortion, provided sampling frequency is more than twice the highest frequency of original signal, that is Fs more than 2 FM. But if this condition is not satisfied, then what happens? This point comes and stays inside the first replica. In such case, filtering out the distortion creating part becomes difficult. A few points regarding aliasing. What is aliasing? It is the distortion in the recovered signal due to overlap in the shifted replicas of the original spectrum. When Fs is more than 2 FM, it distorts the spectrum of the original continuous signal. In this phenomena, higher frequency components of the signal take on identity of the lower frequency ones. Aliasing is a distortion, a type of distortion. It can be eliminated either by increasing the sampling rate or by reducing FM using anti-aliasing filter, which is essentially a low-pass filter. Here is an important statement given. A signal cannot be simultaneously band limited and time limited, but signal can be unlimited simultaneously in both time and frequency domains. So far, we covered the case of band limited signals. Now we consider band pass signals. The spectrum of a band limited signal appears like this. Spectrum of band pass signal, it appears like this. Pass band is there. Lower cutoff frequency is non-zero. upper cutoff frequency is finite. That is band pass signal. Band limited signal is one for which lower cutoff frequency is 0 and upper cutoff frequency is finite. Now we consider sampling for band pass signals. When a band pass signal is occupying the frequency band f1 to f2 with the bandwidth b equal to f2 minus f1, then the sampling frequency is fs is equal to 2b, provided either f1 or f2 is harmonic of fs. That is f1 equal to nfs equal to 2nb or f2 equal to nfs equal to 2nb, where n equal to 1, 2, 3, etc. If both f1 and f2 are not harmonics of fs, then sampling frequency should be in between 2b k by n and 2b k minus 1 by n minus 1, where k equal to f2 by b and capital N equal to 1, 2, 3, etc. This formula has to be adhered if you want perfect recovery of the original CT signal from the sampled one. It can be observed that a band pass signal can be recovered even after being sampled at a rate fs less than 2f2 general. A general formula for minimum possible sampling rate is fs more than 2f2 by largest integer less than or equal to f2 by b. According to the above relation, if f1 equal to 0, the signal becomes band limited signal and sampling frequency becomes equal to fs more than 2f2, which is in agreement with Shannon's sampling theorem for LP signals. If f1 or f2 equal to mb, fs should be more than 2b. It says absolute minimum sampling rate in the most favorable situation is twice the bandwidth of the signal, not the highest frequency. Some more information regarding sampling. Commutator is a switching mechanism which not only samples but also combines them. Decommutator is also a switching mechanism which separates samples belonging to individual signals so that these signals may be reconstructed. So commutator is one which converts, which gives dt from ct. Decommutator is one which separates samples belonging to individual signals. Bandwidth. To transmit n independent baseband signals, each band limited to FM simultaneously require a bandwidth of no more than nfm. Sampling can be instantaneous sampling. It can be natural sampling. What is instantaneous sampling? Here the samples are infinite small duration and energy gives very low level output signal. In natural sampling, the samples are of finite duration. More the level of output signal, it can be recovered by passing the samples through an ideal low-pass filter with cutoff at FM, but it gives rise to crosstalk in the channel. Another information regarding sampling in general. In flat top sampling, the design of the electronic circuitry required to perform the sampling becomes simple, but the baseband signal cannot be recovered exactly by simply passing through an ideal low-pass filter. It results in one type of distortion known as aperture effect. To counter this distortion, equalizer whose transfer function is x by sin x is used in cascade with the output low-pass filter. Signal recovery through holding. To increase the level of the output signal, the sample duration tau should be as large as possible. It can be done at the receiving end after demultiplexing by holding the signal until the occurrence of next sample of that same baseband signal. What is this all about? To understand, consider a continuous time signal like this. DT signal, it is generated by sampling CT at a particular rate. The rate is given by sampling theorem. Now, the sampling can be instantaneous sampling, like value of the function at this instant. So this is instantaneous sampling. Natural sampling is also there. What is that? Natural sampling means sampling of the signal is done during a finite duration like this. So natural sampling results in this kind of flat top sampling is there. It means, let us suppose sampling is done here. This value, this particular value, it is taken and the signal is sampled like this. Notice, in a natural sampling, the top of the sample follows the variation of the CT. In flat top, its value is fixed. Flat top sampling results in one type of distortion called aperture effect. Of course, this distortion can be eliminated to some extent using a circuit called equalizer. Now, last point here is signal recovery through holding. In all these sampling methods, the width of the sample is usually small. So, energy content in the sample is very little. To make the sample strong, what normally they do is they increase the duration of the sample by holding the signal until the occurrence of the next sample. By this process, they are able to increase the level of the output signal. It's a kind of amplification. With this, we come to the end of this session. Before closing down, let us recollect important areas that are touched upon in this session. Historical development of sampling theorem, statement of sampling theorem for band limited signals, statement of sampling theorem for band pass signals, different types of sampling mechanisms, and some more aspects of sampling are also introduced, discussed, described in this session. Hope this session is useful to you. We meet again in another session with a new topic soon.